Before I discuss the mathematician's version of the word span, the linear algebra version of the word span, I want to bring your attention to one of the Merriam-Webster English versions of the word span, and that's this one: to extend across. The analogy that we're going to be using in math with this definition, we're going to have a set of vectors that in a sense will extend across some space, extend across a plane, extend across a line, extend across a three-dimensional space, a four-dimensional space. Definition. If S equals V1 through Vk, so if this set is a set of vectors in Rn, then we call the set of all linear combinations of V1 through Vk is called the span of the vectors V1 through Vk. It's written span of V1 through Vk, or sometimes span of S, to emphasize the name of the set. In this case, the span of the set S is equal to all of Rn. We say that the set S is a spanning set for Rn. Let's return for a moment to our analogy with the Merriam-Webster definition of span. The idea is that the set of vectors v1 through vk extends across its span. In other words, the vectors v1 through vk extend to everybody in their span by taking linear combinations. Let's start with a prototypical example. And that's the vectors E1 equal to 1, 0, and E2 equal to 0, 1. These form a spanning set for R2 because for all vectors A, B in R2, we can express the vector AB as a linear combination of E1 and E2 by A times 1, 0 plus B times 0, 1. Alternatively, we can see this because of theorem 2.4. Putting the vectors 1, 0 and 0, 1 into the columns of a matrix, and then augmenting that matrix with the target vector AB, we get a matrix which is in reduced row echelon form, and noticing that this is consistent, which we can see from the fact that it's in reduced row echelon form, and there is no row which is all zeros to the left of the bar and and not 0 to the right of the bar, we see that this is consistent. And therefore, by theorem 2.4, this vector here is a linear combination of the columns of these two vectors. Or in other words, this vector here is in the span of these two vectors. Similarly, the standard unit vectors E1 through En of Rn form a spanning set for Rn. Let's find the span of the vector u equals 1, 2, 3. By definition, the span of u is the set of all vectors x equals tu for t in R. And this should seem kind of similar to some things we've seen before. Earlier in the course, instead of using the letter u here, we would have used the letter d for the direction vector of a line. So in other words, this is the line through the origin with direction vector u. Let's find the span of the vector u equals 1, 2, 3 and v equals 4, 5, 6. I know I'm very creative with these numbers. By definition, the span of the vectors u and v is the set of all vectors x equals su plus tv for s and t in R. And again, this should be looking familiar. This looks just like the vector form for the equation of a plane in R3. But there's one thing that we have to make sure before we can conclude that this is in fact a plane. And that's, we need to make sure that these two vectors u and v are not parallel. Well, just looking at these, neither is a multiple of the other, so indeed the vectors u and v are not parallel. So since u and v are not parallel, we can conclude that their span is a plane, and we can choose one particular point in that plane as to be the base point. We might as well take s equals 0 and t equals 0. So, which gives us x equals 0. So this is the plane through the origin with direction vectors u and v. One last example, and that's to find the span of 1, 3, 2, 4. By definition, we can use the same definition that we've been using. We can root something like this, noting that, okay, this is the set of all vectors which can be written as x equals s times 1, 3 plus t times 2, 4. But taking a hint from over here, we see from over in this previous example Oh, I forgot to write a v over here. Oops. So taking a hint from this previous example, these two guys are not parallel, and this expression here suggests that their span should be a plane. But the only plane that is contained in R2 is R2 itself. So intuitively, these should span R2. To see this algebraically, we can use theorem 2.4. Putting these vectors into a column, into the columns of a matrix, and putting A, B on the right side. So actually, let me specify. Let AB be any vector in R2. And I want to show that this vector is a linear combination of this one and this one. That's the definition of span. So I can use theorem 2.4 to do so. Well, I start over here by putting 1, 3, and 2, 4 into the columns of a matrix with AB on the augmented part. Then I can use row reduction. I can use Gaussian elimination. I can do row 2, replace that with row 2 minus 3 times row 1. And when I do that, I'm going to get a 1 here. Let's see, still a 2 here and an A here because I didn't operate on row 1. For row 2, I have 3 minus 3. Okay, that's 0 as I hoped. And 4 minus 3 times 2, so 4 minus 6 is negative 2. And B minus 3A. The important thing to note here is that this matrix is consistent. This guy, we can see, this system is consistent because there is no row which is all 0 to the left of the bar and not 0 to the right. So we have consistent. And since this system here is consistent, our original system is consistent, or in other words, that means that AB by theorem 2.4 is a linear combination of 1, 3, and 2, 4. So therefore, by theorem 2.4, AB is a linear combination of 1, 3, and 2, 4. Now, later on in this course, we will find an alternative way to describe the span of a given set of vectors, and that's going to be using bases. But we'll talk more about that when we get there.